Hello everyone, welcome to this workflow demo on how to calibrate optimal IPMSM control using Model-Based Calibration Toolbox. My name is Dakai Hu, and I am a MathWorks application engineer. This workflow demo is based on MATLAB version 23b. So if you are using an earlier version, the steps could be different because we had some major updates to the tool for 23b. Before we get started, I'll explain the two types of torque control lookup tables that we're trying to calibrate using Model-Based Calibration Toolbox, or MBC. The first one is the speed-based tables. Inputs to these tables can be absolute torque and motor speed, or we can use percentage torque instead of absolute torque. Because each table is calibrated based on a fixed DC bus voltage, VDC here, if VDC is a variable, we need to calibrate multiple pages of these lookup tables. And the algorithm will need to interpolate between different bus voltage levels. The second type of lookup table is the maximum flux linkage based lookup tables. In this type of algorithm, we first use VDC and speed to calculate the maximum allowed flux linkage, which then become one of the inputs to the lookup tables. Here, VDC is already considered in the equation to calculate lambda max. Therefore, for this algorithm, we don't need multiple pages of lookup tables to account for the variation of VDC. In this tutorial, we will focus on calibrating the speed-based lookup tables. If you'd like to learn how to calibrate maximum flux linkage-based lookup tables, and you need some help, please reach out to me directly. My email is listed in the beginning of this video. Okay, I will open up MATLAB and we'll get right into the tutorial. In the provided workflow example, we will include a 150 kilowatt PMSM characterization dataset. This dataset contains PMSM characterization data that are dyno tested and are arranged by columns. The first column is ID current, and the second column is IQ current, then followed by flux linkage D and flux linkage Q, and the last column is measured torque. Together, we will also provide a data preprocessing script, which is a MATLAB live script. We need this script to preprocess the raw data, rearrange it by torque and speed operating points, and then place it in a column format that's required by the MBC toolbox. Here in the live script, you will find a chunk of code which uses the contour function to plot different torque contours, which is right here, and rearrange data by these torque levels. The data is then copied for each speed operating point, because we need speed information to calculate voltages in order to implement a voltage constraint throughout the calibration process. Here, after generating the Excel data file, we'll have everything we need to go through the model-based calibration workflow. Our development team come up with an API script that invokes MBC Toolbox in the background, which generates the final calibration tables using a single function called Calibrate PMSM. I suggest that you go through the entire MBC workflow first to understand each and every step in the MBC toolbox, and then come back to try this single point API function Calibrate PMSM. After running the data preprocessing live script, we'll generate this PMSM_MBC data file, and we'll import this data into the MBC toolbox, which we can access from here in the apps gallery. We'll select MBC model fitting. Here, we'll select import data and make sure file is selected. Click OK and choose the PMSM_MBC data file. Once your data is in the MBC data editor, the first step we do is go over here and create filters. We're going to add a voltage filter. For the voltage constraint, the maximum modulation voltage is 222.8. And here, for the raw data, we're going to give it a 20% margin. And then we'll also add a current filter. Here, current filter constraint is 615. And the same way, we're going to add a 20% margin. Now we're going to click OK. If you go to the summary section, you'll notice that a lot of the raw data has been filtered out. We're left with around 15,000 data points. We're implementing a 20% margin here for the filtering because we want the fitted models in the next step to be able to extrapolate beyond the original voltage and current limits. From here, we're going to click the check mark. Click yes. So the next step is to fit models to the data we have. Click Fit Models. Here in the Fit Models dialog, you'll see some templates set up. Ultimately, we want to use the point-by-point model. In this case, there's already a IPMSM speed model template set up for me. So I'm going to select that. When I select that, you will see that the responses, local inputs, and operating point inputs has been pre-populated. Here, we're selecting speed as the operating point inputs. And the local inputs are ID and torque. Response surfaces are IQ and VS. Make sure that the fit boundary model checkbox is selected. From here, we're going to click OK. In this Define Operating Point Groupings page, we have to set a tolerance for speed. In our example dataset, speed has precise increments of 250 RPM. Sometimes if your speed information is a measurement from the dyno, for example, then it is not always precise multiples of 250. For instance, you could have a speed point of 1000 RPM, another point of 1005 RPM. From a model fitting and calibration perspective, we want to group these two speed operating points as one using a tolerance of 5. In our example, any tolerance number below 250 is fine. So here I'm just going to set it as 10. And then I'm going to click OK. Now model fitting process will start. If you have parallel computing toolbox, this process will be automatically distributed into different cores of your PC, which saves time. In my case, with parallel computing and 4 different cores, this process takes slightly over a minute to finish. Once model fitting is done, you can come to the model browser and look under IPMSM speed. And you'll find IQ and VS models under different operating points. Keep in mind that we have altogether 37 operating points of speed. So for each operating point of speed, we have one set of IQ and VS models. We can look at each one of them. For instance, this is the IQ and VS model at this particular operating point, which is 8,250 RPM. You can right-click and print the plot to a figure file. From here, the next step is to import these models to calibration. To do that, we're going to highlight the project, which is untitled, and then we're going to click Generate Calibration. This dialog will pop up, Import Models to CAGE. CAGE stands for Calibration Generation. From here, we're just going to click OK. Now in CAGE browser, you'll see the IQ and VS models are listed in here. We have 2 tasks in CAGE. The first one is to use Cage to find the maximum torque speed envelope for this IPMSM motor through optimization. Because Cage can only optimize models, so the first thing we have to do is to set up a few function models. To do that, first make sure you're in the Models tab. And here click New Function Model. The first function model we're going to create is IS, which equals square root of ID squared plus IQ squared. Units is ampere, which is optional. Click Next. Make sure all the inputs are assigned properly. And then we're going to click Finish. Next, we're going to set another function model, which is torque model. So we're going to click the function model again and type torque model, which equals torque. Make sure torque is assigned and click Finish. We need to store the torque speed envelope in the lookup table. So let's create the 1D lookup table first. To do that, go to File, go to New 1D lookup table. Here, I'm going to type torque envelope. The row is speed. And remember, we have 37 speed operating points, starting from 1000 RPM to 10,000 RPM at increments of 250. Okay. Now this 1D lookup table for torque envelope is created. Next, we need to create an optimization to actually find the torque speed envelope. So we're going to click Optimization and click Create Optimization. Here we want to maximize torque model under the constraints of current and voltage. So click Next. We're going to select Maximize, and we're going to click this plus button to assign the constraint. The first one is current, which in this case is 615 ampere. I'm going to also add the voltage constraint, which is 222.8 volt. The operating point will be the breakpoints of the torque envelope, which is speed. So free variable will be ID and torque. Speed is the only fixed variable. Click Finish. Okay, so at this page, the optimization has already been set up. We have the constraints listed in here, and we have the objective listed in here. Our objective is to maximize the torque model, in the meantime conforming to these constraints. So from here, I'm just going to click Run. Again, if you have parallel computing, this process is very short, somewhere around 10 seconds. Here is the optimization results. When you look at the results curve, you'll find these green squares, which indicate that optimization converged at those operating points. Here we can select x-axis to be speed and y-axis to be torque. You can open this torque envelope in a separate MATLAB figure file by right-click and select Print to Figure. So this is the torque speed envelope that we want. Next, let's fill the lookup tables with these optimization results. Notice here the torque envelope table has already been selected. We're going to click Next and fill that with the torque model results. And then we're going to go to the lookup table section And you'll see the results are in here. So here I'm going to click Save the project. I'm going to give it a name, Cage Project. The best practice is to save your project often so that you don't lose any progress made. Now we have our first optimization done, and we're able to find this operating torque speed envelope under voltage and current constraint. The next step is to use this torque speed envelope to set up a function called torque grid. Torque grid is calculated by the percentage of maximum torque at every speed. To create torque grid, we're going to go to Models, and again, create a new function model. I'm going to type torque grid, which equals torque percent divided by 100, then times the torque envelope. Units will be Newton meter. Click Next. Here, torque percent is a new variable that will be created automatically. Here, I'm going to click Finish. The reason we need to create a torque grid is because we want to use torque grid to set up operating points for the final ID and IQ optimization. Here in the Cage browser, right-click the model IQ and then select Added Inputs. I'm going to update this torque input with torque grid. And click OK. The tool recognizes that some other function models also has the same input of torque, so it asks if we want to change those as well. We're going to select Yes. Now you'll see some model duplicates have been created. There's an IQ model duplicate, an IS model duplicate, and also VS model duplicate. They're all assigned the name _torque grid. Remember, torque grid is calculated by torque percent. Therefore, by swapping those torque inputs with torque grid, we are now inserting torque percent as one of the function inputs for IQ, IS, and VS. During the next step, we will create a function model called TPA, or torque per ampere. Again, we're going to click Create a new function model and type TPA equals torque grid divided by IS _ torque grid. Units will be Newton meter per ampere. Now we have created all the function models we need. Before we set up an optimization to generate ID and IQ current tables, we need to create lookup tables with appropriate breakpoints. Specifically, we need speed and torque percent as breakpoints. Here in the Cage browser, I'm going to select Lookup Tables and Trade-off. In this Create Lookup Tables from Model dialog, I'll highlight IQ torque grid and click Next. Here, speed is one of the breakpoints. For torque percent, which is the other operating point, we have to set it up here. I'm going to give it as a free-form vector and start with 1% and then in increments of 4, all the way to 100%. We can come in here and update the names for IQ table. Just going to call it IQ _ table, which is consistent with the ID _ table. Click Finish. Now you'll see the ID and IQ tables are created. Okay, from here, we are now ready to set up an optimization to find optimal ID and IQ currents. To do that, click Optimization, highlight the project, and click Create Optimization. You're going to highlight TPA. Next. Our goal is to maximize TPA. We need to set the same constraint as before, which are current constraint and voltage constraint. So for current, we select is_torque grid. That is 615 ampere. For voltage, select vs_torque grid. That is 222.8 volt. For the operating points, we're going to select breakpoints, which are speed and torque percent. Now, one last thing here, we have to decide what are the free variable and fixed variables. In this case, the fixed variables are torque percent and speed. So we only have to highlight ID to be the free variable. In this page, we just need to double check that the optimization has been set up correctly. We are here to maximize TPA, and the constraints are TPA boundary constraint, IS constraint, and VS constraint. Now, before we actually run the optimization, we need to set up the optimizer. Here, I will go with the default optimizer, but I will change the number of start points from 1 to 2. This will give us a higher chance of finding the global optimization solution. And then click Run. Depending on whether you have parallel computing or not, this process can take somewhere between 2 minutes to maybe about 10 minutes. In order to save time, here I'm going to speed up the video. Now optimization converged. We can come here to check the result. This is the ID table. And we can also pull up the IQ table. In this case, everything is green, which means that every single operating point has converged. Sometimes you may find some red dots in here, which indicate that the optimizer couldn't find a solution. If that happens, you can come to the results table and locate exactly which operating point failed. For example, this one. And then you come to the constraint summary section and see if any constraint has been violated. When this constraint value is negative, that means every constraint is satisfied. When that value is positive, then that means that constraint is probably violated. However, we do have a tolerance set up for that. In this case, for example, this constraint value is positive, but it's in the order of 1e minus 5. It's a quite small value, which is within tolerance, so it's still considered satisfied. Occasionally, for certain violations, you will see that the constraint value is in the order of 1e minus 4. And if that's acceptable to you, you can come here and manually check this accept box. Okay, so from here, we can fill in the lookup table with the optimization results. Click Fill Lookup Table. The two tables are already in here. Next. Those are correct. And we click Finish. Then you can come to the lookup table section. You will see the ID and IQ tables filled up. This is the ID table. And this is the IQ table. Okay, we're back to the optimization page. So if you're following every single step in this tutorial, and you're still getting a lot of failed optimizations, don't hesitate to reach out to us for help. As a summary for the entire IPMSM model-based calibration process, we started with using a live script to pre-process IPMSM characterization data. Then we fitted models in the MBC model fitting app. Afterwards, the models were imported into calibration generation, or CAGE, to create an optimization to find the torque speed envelope under voltage and current constraints. Then we created torque percent and torque grid variable so that we could have torque percent as breakpoints for the final ID and IQ table. And eventually, we created an optimization to maximize torque per ampere under both voltage and current constraints. And finally, the optimized torque speed envelope, as well as the ID and IQ tables, are exported into external files. So where can you learn more about this topic? I published a technical article documenting some domain knowledge for this workflow. For those of you who want to dive a little deeper on the theory side, you can reference this article on the MathWorks website. Thank you very much for watching this tutorial.